into the magnetic shoe project, let's just go to a brief introduction. So, different types of renewable energy are being used nowadays. But it turns out there are still other types of renewable energy that have never been tackled before. One of them is the human energy, or more precisely, the energy involved in walking. You see, people walk to work, people walk while they're practicing exercises, people walk essentially to everywhere they go, and they do it every day. So it might seem insignificant, but considering the amount of people that live today in the world and the amount of time that each person spends every day walking, this walking energy should be considered. So it essentially consists of two major features. The first one is to provide a damping mechanism, and the second one is to harvest clean and renewable energy. The damping system is pretty straightforward. We'll use the magnetic repulsion to oppose to the gravitational force, thus providing the damping. The energy harvest, though, relies on the principles of Faraday's law. So, for instance, if you vary the magnetic flux in a closed surface, you will induce an electrical field there. If the surface is conductive, there will be a current generated too. We will use that to convert a person's mechanical energy into electrical energy. Before getting in depth in those topics, let's take a general look at the shoe.
Here is a simplified model of the shoe, made using Tinkercad. Due to limitations of the software, one important detail was omitted. There is a slight longitudinal curvature in the shoe surface to proportion a more natural stepping motion. Having that said, let's see the parts of it. First, we have the main structure of it. The idea here is that the upper panel will slide down when pressed by one's foot. The permanent neodymium magnets then come in play. They were placed in the points where our foot exerts the highest pressure. Those magnets will repel each other and create a damping mechanism. Next, we have the coils and the neodymium magnets. Those two are the ones responsible for the generation of energy. Here, we can see the principle of functioning. The magnet will move up and down as the person walks, and as a consequence of this motion, a current will be induced in the coil. After that, this current can be used to recharge batteries, light up LEDs in the shoe, or any other electrical device. Note that we want the maximum efficiency here. The thing is that the shoe is more often horizontal than a vertical object. That is why the coils were put in the horizontal. To maximize the energy generation though, we will seek for the biggest coil area possible. With a few adjusts, the coil and magnets were changed to broaden the whole shoe's lateral surface. This way, not only the shoe will be more efficient, but while the upper coils are not working, the down ones will be, and vice versa, providing a constant power.
Now, imagine you're casually walking in the park. We will try to estimate the energy generated by that with the magnetic shoes.
Let's be a little more quantitative about this. First, we define the magnetic field density as the total magnetic field of the magnet over its length. Then, we define the area of the coil as N times S. Well, N is the number of spires the coil has, and S is the area of each spire. We will also assume that the magnet moves with a mean velocity v. Now we can use Maxwell's equation to compute the potential difference. Note that the up and down motions are similar, since we're only interested on the variation of the magnetic flux. Now we have to estimate this mean velocity, the area of the coils, and the magnetic field density. We'll use a coil of 20 spires and an average human foot length of 0.26 meters. Considering the coil height as 0.02 meters, we get the coil area as 0.26 times 0.02 times 20. Using our neodymium magnet field as 1.5 Tesla and its height as 0.02 meters, we can compute the magnetic field density. Finally, for the mean speed, I counted the number of steps I would take in 120 seconds. It turns out that I took 203 steps. This yields an approximate speed of 1.7 steps per second. Assuming that a foot maximum height while walking is 4.5 centimeters, in each step, which involves going up and down, your foot will cover 9 centimeters. With this data, we can compute the average vertical velocity of your foot. With that, we can finally compute our potential difference.
Well, we can now see that the magnetic shoes brings a lot of benefits. First, it provides a promising durable damping system, which accounts for a more durable sneaker, leading to a more conscient consumption of shoes. Well, of course, the potential difference calculated is just an estimation. The potential difference is definitely not constant, as the magnet speed is not constant either. But it gives us a reasonable notion of this renewable energy potential. The efficiency actually doubles if we account for the 2 feet, and there's still a lot of room for improvement. It gets even higher if we account for the number of people living out there and the hours spent walking. So it's definitely something that should be studied, and that's precisely what science works for: a better life quality in a cleaner world.